I'll go over the gravity problems if I have time at the end, and also we'll continue. We're going to do sort of double tracking next week. We're going to talk about finish up with gravity and start vectors, just so we get off of those equations. Okay, a vector. The shortest thing a vector is, shortest way I can describe it is a vector is an arrow. And that arrow is used to represent, that's what all the books say, a magnitude and a direction. These start simple, get complicated pretty quickly. Magnitude and a direction. What does magnitude mean?
Bigness.
Bigness is actually the most literal definition. It's often will be speed. That's what we've used it for already a little bit. Magnitude, I'm going to use that exact word.
Bigness.
Bigness. Amount of bigness. Could be negative bigness.
You can't use a word from an outsider.
Darn.
Mrs. Punjab.
Alright. Size, we'll call it.
I missed all of that.
Direction should be self-explanatory. Now, since I'm going to start talking about vectors, I have to compare vectors to things that are not vectors. A scalar only represents magnitude. Only represents magnitude. So a scalar only represents size or quantity or magnitude. In other words, a scalar is just a number. You've been working with scalars all along, but now we have something to compare it to. I can now give you a new definition, actually. Okay? Velocity is a vector. Speed is a scalar. Remember we've said that velocity can be positive or negative, but a speed is always positive?
Wait, does that say for scalar magnitude?
Scalar?
Scalar, yes. It's spelled like scalar. It means magnitude, size, or number. It's just a number. So when I talk about speed, how fast something's going, that's a scalar. All that is a number. When I talk about velocity, we've been just using left or right or up or down. That can be positive or negative. That has a direction to it. Now we're going to start talking about velocities and things that can be up, down, left, right, at an angle, all over the place. It's when we stop getting one-dimensional and start getting real.
Snap back to reality.
Oop, there goes gravity. Well, anyway, sorry.
Be sure to put on the works cited.
Exactly. I love that song. Okay. Any questions on this real quick?
Ray.
Vectors are going to be arrows.
Can you graph them? Will they be arrows in a graph?
They're mostly on the Cartesian coordinate plane, and there's just a couple things you need to remember about them. And that's exactly what I'm going to do next, graphing vectors.
Yay. Wow. I like completing each other's thoughts.
I know. You complete me.
Wow.
Okay.
Are you recording that and putting it on YouTube?
Sure.
That's
That doesn't worry me.
Well,
Okay, vectors.
Yeah, where's the camera?
Yeah, where is the camera?
Right there.
It's
Okay.
inside.
Graphing them.
Graphing.
First thing you need to know about a vector is independent of location. A vector is independent of location.
That means it doesn't exist.
Now, it means it doesn't matter where it exists. Okay? So,
Wrong.
Mrs. Punjab.
it's going to be, this is on wheels. Okay, I'll give you a quick example of that, very quick, before I go on to it. Vectors in physics are most commonly used to represent forces. Okay? A force for now, I just want you to think of it as a push or a pull. Okay? As far as this cart is concerned, try and put yourself in the perspective of a cart. Be one with the cart.
Rene Descartes.
Rene Descartes. Yes, we're going to call this cart Rene. As far as Rene's position is, okay?
So it's a brown rat.
Yes, exactly. If I'm pushing on Rene, causing it to move,
That's not nice.
or if I'm pulling on Rene, causing it to move,
What if you're hitting on it?
If it's Renee,
Stop.
would it be a he?
stop, focus on this. If I am pushing or pulling on the cart, does the cart care which?
No.
No, not particularly. The cart, it doesn't matter the cart. Johnny, sit down and stop.
Okay, I'm sorry. I'm just
Now, okay, so if I push on the cart in that direction, or if I stand on the opposite side of the cart and pull it, Doesn't matter. There's no difference. That's the idea behind vectors being completely independent of location.
But there is a difference.
Not as far as the card's concerned. Remember, physics starts out being about oversimplifying things.
Well, that makes no sense anyways, because a car can't be conserved. So.
But Renee can.
I know. I'm sort of.
Renee would be.
I'm
if you
taking
were
the
pushing a car
idea of
line.
frame of reference, and I'm sort of doing what's called anthropomorphizing and
A double what?
So what
treating
does,
the cart like a person.
what does
But
independent
a
of
person
location
would
have to do
care
with
if you
this?
were pushing.
Here's what it has to do with it.
I don't care.
Here is a vector, okay? I'm going to start this vector at the origin, and I'm going to say that its tip is directly above 3 on the x-axis and directly next to 2 on the y-axis. Now there's a lot of ways to write this vector. Here's the simplest. I'm going to call this vector A, and to know that I'm talking about a vector, not any other use for the many letters in math and science you've learned, I'm going to put a little arrow on top of the A. And now we know I'm talking about the vector A, okay? And I want to describe this vector. Don't think your book quite uses this notation. I'm going to use the notation from the pre-cal book for now.
Does the arrow tell us which way it's going, or is it just a sign for vector?
Good question. In this case, it's just a sign for vector.
Do you have to label the vector with an A?
If there's more than one on the graph, yes. But for now, this is the only vector there. Now, I'm going to label this vector, don't write parentheses yet, wait till I'm finished to write this down, by where the tip is compared to the origin. So it's going to be 3, 2. Now, how do I know I'm talking about a vector and not a Cartesian coordinate point? In addition to the A, I'm not going to use parentheses. I'm going to use those funny-looking brackets.
The little cute ones.
My little cute ones.
So does a vector, does it just end right there?
Just ends right there.
Says
But it
vector
has
on
an
the
arrow.
Yes.
Why do you want to
So
know?
they don't
Does it have to
just
have an
keep
arrow?
going?
Has to have an arrow. Has to have an arrow.
But
Has to
doesn't
indicate
that
direction.
always mean that it
I
keeps
mean,
going?
no, the arrow means
Hold
it
that
keeps
thought.
going.
No, this is different. Very good questions. Excellent. You got to put everything you learned in geometry out of your head. This is not a ray.
That'll be easy. I didn't learn geometry.
So some that'll be easier than others. That's true. Okay. This is not a ray. This does not mean it keeps going on forever. The vector does stop, but that arrow does indicate direction. We need to have that arrow there, and in a minute I'll tell you why. But first, I want to talk a little bit more about this vector A here. Now, if I draw another vector, actually I'm going to draw multiple vector A's. I'm going to call them all vector A if they have certain things in common, and here are those things. I'm going to start at the point -2. Extend this a little bit. I'm going to start at this point -2, 3, -2. Here's the point on the Cartesian coordinate plane where I'm going to start. I know it's a point because I'm using normal parentheses to describe it. From that point, I'm going to go over 3 units and up 2 units, which takes me up here to this point, which will be 6, 0. And I'm going to draw another vector with its tail, the end without an arrow, down here at 3, -2, and its tip up here at 6, 0. In order to get from here to here, I went 3 units right and 2 units up. This vector is identical to unit A. It does not matter that their tails are in different places. This is also the vector 3, 2. Anywhere on the Cartesian coordinate plane, if I pick any point you can imagine, and from that point, I go 3 units over and 2 up, and I put the tail down at this end and the tip up at this end, that is the vector A. They will all be the vector 3, 2.
Because they're parallel.
Because they're parallel and they're the same size.
Because they have the same slope.
Yes, the slope is
Because
an
they're
important thing
parallel.
and the same magnitude. They have the same magnitude and direction. Slope is a great way to think of this. I was going to mention that the better you understand slope, the easier this might be to understand vectors. Now, if the tip, here's where it's very much like slope. Now I'm going to talk about another vector over here. Actually, you know what? I'm going to put it right here. No, I won't. That'll be a little too confusing. I'm going to start a vector at -1 on the x-axis, and from that point, I am going to go down 2, and I'm going to go out to -4. How would I describe this vector?
It's facing the opposite direction.
No,
but it's
it would
going
be
the
the
same amount
same.
and has a negative slope.
It would be, no, it wouldn't have a negative slope. It's got the same slope because they're both negative.
It would be a negative vector.
How would I? Well, you did this last year. You better know this, Jenny. How would I describe this vector in terms of these funny little brackets?
3, 2.
Exactly wrong.
Negative 3, negative 2.
Negative 3, negative 2.
But they're both negative.
So,
So that's
facing
true.
the opposite direction.
Yeah.
It's facing the exact opposite direction. What that tells me is if I'm representing a force or a
Oh.
velocity, that tells me this force is in the exact opposite direction of this force.
so if you're going up and to the left, it could be positive. No, it would be
Negative
negative
3.
and then positive.
Yes.
It's negative, positive, because it's
Correct.
Yeah.
So the slope matters, but they mean different things. Unlike slope, where you put them in a fraction over each other and a negative over a negative makes a positive, unlike slope, here the negatives are important. They have to stay negative to tell you that this force is pulling in this direction. Okay? The trigonometry is going to kick in a couple minutes here. There is another way to think of these vectors. Let me know, may I erase this bunch of vectors here?
Yeah.
Okay. So that it doesn't matter where you put it. Does not matter where you put it on the coordinate plane. Location was never mentioned in that description. The vector 3, 2 can be anywhere in the Cartesian coordinate plane. It just means go over 3, up 2. If they're negative, it means go down, go left 3, down 2. If one's negative, one's positive, then it'll go to the appropriate angle. Here's another way to think of vectors. If you have a horizontal vector with a length of 1, this vector gets a special name. And this is going to be confusing a little bit. This is your I vector. It's called a unit vector because it's 1 unit long.
Is that an I?
Yeah, is that an I?
What is that?
This is a cursive I, sort of.
A cursive I?
Oh, like
It's meant to be. Like a fancy I.
A fancy I?
like
Stop
imaginary
repeating.
numbers.
Pardon?
Like imaginary numbers. I.
Yeah, you know, it's the same. It's written the same way, but with the arrow over it, you have to know you're talking about a horizontal unit vector, and without an arrow over it, you have to know that you're talking about the square root of -1.
It looks like an E.
It looks like a J.
Okay. Now I equals 1, 0, because it is a vector that represents something going 1 unit to the right and no up or down. Okay? If you have a vertical unit vector, 1 unit long, that's called J with an arrow over the top. Incidentally, if any of you go into electrical engineering, J with no arrow means the square root of -1.
That's annoying.
They just changed the letter between engineering and math.
Why?
I don't know. I've never gotten an answer to that.
Because it's a gerund.
I have no idea. So this J would represent the vector 0, 1. So this gives us another way to write our vectors. So the vector,
That one's going up and down, right? I'm
yes,
gonna
this
go
one's
do
going
my-
up or down.
I'm gonna go do my history.
Hey, how do you know?
Okay. There's more coming up, but it's all trick stuff.
Oh,
Vectors
now
make
I
triangles.
remember J's and I's.
Oh yeah, of course they do, because
Yeah.
then you have, that makes
So
sense.
I can also write 3, 2 can also be written as 3 I vectors. You go 3 single